Hello. In the previous lecture, we were doing functional equation. In this lecture, we are going to do a couple of questions. Okay, so let us start. So we want to determine all function from R to R such that 2 times f of 2x is equals to f of x plus x and f is continuous at 0. We want to find all these functions, okay, from R to R. So what will happen? See, first thing first, at x equal to 0, what will happen? It will be 2 times f0 is equal to f0 plus 0. It implies f0 will be equal to 0. So clearly at x equal to 0, function is 0. Now what I'll do, I'll simplify this particular question. That is f of 2x is simply equals to 1 upon 2 f of x plus x by 2. Okay. So what is f of x then? F of x is simply replacing x by 2 here. So it is 1 upon 2 f of x by 2 plus x upon 2 square. Okay. If f of x is so and so, then what is from here I'm just writing here, what is f of x by 2? So what will be f of x by 2? Instead of x, if I write x by 2, this will be, if I write x by 2 here, it will be 1 upon 2 f of x upon 2 square plus x upon 2 cube. So instead of f of x by 2, if I write this entire thing, what I'll get simply f of x is equal to, this 1 upon 2 is already there, just don't forget it. This will be 1 upon 2 square f of x upon 2 square plus x upon 2 raised to power 4, because this 1 upon 2 will follow this, and then x upon 2 square. What will be f of x upon 2 square? Okay, so if I just replace x by 2 here, I'll get f of x upon 2 square. If I just replace x upon 2 here, so I'll get 1 upon 2 f of x upon 2 cube, and instead of x, if I replace x by 2, this will be x upon 2 raised to power 4. So what will be fx now? So fx will be now equals to 1 upon 2 square is already there. You don't have to forget this 1 upon 2 square, and f of x upon 2 square, f of x upon 2 square is 1 upon 2 f of x upon 2 cube plus x upon 2 raised to power 4, now plus x upon 2 raised to power x upon 2 raised to power 4 plus x upon 2 raised to power 2. So what will be our fx? Fx will be simply equals to 1 upon 2 raised to power 3 f x upon 2 raised to power 3 plus x upon 2 raised to power 6 plus x upon 2 raised to power 4 plus x upon 2 raised to power 2. I don't think there is an issue till here. Okay. So in general, I can write my fx as I go on. It will be 1 upon 2 raised to power n f of x upon 2 raised to power n, and this will be, what is 6? 6 is nothing, 3 times 2, so this is x upon 2 raised to power 2n plus x upon 2 raised to power 2n minus 1 dash 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 x upon 2 raised to power 6 plus x upon 2 raised to power 4 plus x upon 2 square. I already know that function is continuous at 0. So x upon 2 raised to power 2n, it converges towards 0 for all x belongs to R. So since function is continuous at 0, then f of x upon 2 raised to power n converges towards f of 0, which is certainly 0. So as n tends to infinity, this converges to 0, and as x tends to infinity, this will be equals to what? Fx will be equals to x into 1 upon 2 square, 1 minus 1 upon 2 square. Certainly this is equals to what? F of x will be simply equals to x upon 3. So this particular function, which is linear x upon 3, satisfies this functional equation, given that it is continuous at x equal to 0. Now, on similar pattern, one can do another question. Now, this is a question which is in two parts. The first part I'll solve. Second part I'll ask once I have solved. Okay. So once I'll solve it, then the second part I'll ask when it is solved. Okay. The question says that let f be defined from 0 comma infinity to r be a function that satisfies f of x is equal to f of x by 2 plus 1 for all x belongs to 0 comma infinity. The first part asks you this: there exists a point p belongs to 0 comma infinity such that if f is continuous at x equal to p, then f is continuous on 0 comma infinity. So one asks that if f is continuous at certain point p, then f is continuous on 0 comma infinity. Okay, and this is the functional equation. So this has a similar approach as we have done in the previous. So we know that f of x is equal to f of x by 2 plus 1. Let's say this is y. So this will be equals to what? F of y upon 2. So this will be f of, let's say this is your z. So this will be equals to f of z by 2. This, let's say w. So this is f of w by 2 plus 1. So if it goes all along, so I can say that f of x will be equals to what? F of x will be f of x upon 2 raised to power n plus 1 upon 2 raised to power n minus 1 plus 1 upon 2 raised to power n minus 2 dash 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 1 upon 2 square 1 upon 2 plus 1. Let's say this is your yn, and from simple mathematics you can prove that limit yn will be equals to 2, because as n tends to infinity this will go towards 0, x upon 2 raised to power n, as n tends to infinity this will go towards 0, and this particular sum of in form of a gp, this will tend towards 2. So this yn, this particular yn, if I'm saying, this will converge to 2. Now say if f is continuous at x equal to p, it is asking, I'm saying that if f is continuous at 2, if f is continuous at x equal to 2, then every sequence which converges toward 2, every sequence Sn which converges towards 2, f of Sn must be equal to what? F of 2. Now there is a sequence yn which converges towards 2. So if f is continuous at 2, then f of yn must be equal to f of 2. And f of yn is equal to what? F of x. It implies that f of x will be equals to f of 2. And it implies that f of x will be a constant function. And it necessarily implies that f is continuous. So clearly this statement is true. That is, there exists a point p. Yes, there exists a point p belongs to 0 comma infinity. Yes, which is equals to 2, such that if f is continuous at x equal to p, the p is 2, then f is continuous on 0 comma infinity. Clearly, because if f is continuous at 2, then every sequence converging towards 2, let's say Sn, will have this kind of thing that f of Sn will be f of 2. So this particular sequence converges towards 2. If f is continuous at 2, then f of yn must converge towards f of 2, and f of x will then be equals to f of 2. F of 2 is a constant function. F of x is a constant function. F of x is a constant function means f is a continuous function on 0 comma infinity. So clearly this statement is true. Yes, there exists a point p, and this point is p is 2. Now one can ask, is f necessarily continuous? Is f necessarily continuous? Certainly not. I've asked you that if this is the functional equation, then if f is continuous at point p, then f is continuous. Yes. If f is continuous at 2, then f is continuous. Now comes the question that if f necessarily continuous, that is, if f follows this kind of definition, f of x is equal to f of x by 2 plus 1, is f necessarily continuous? Answer is no, false. Why? Just construct an example which is discontinuous at 2, because we know that if f is continuous at 2, then f is necessarily continuous. So what I'll do, I'll simply try to bifurcate this. So at 2, take as 1, just simply I'm, uh, I'm just using this particular function. Clearly, does it follow this kind of definition? I'll just show you. So let us first write x belong when x belongs to 0 comma 2 union 2 comma infinity. So let us just do this. So if x belongs to 0 comma 2, I know what is fx. Fx would certainly be equals to 0, because if x belongs to 0 to 2, fx is 0. Now if x belongs to 0 to 2, f of x, if x belongs to 0 to 2, what will be x by 2? X by 2 will lie between 0 and 1, and x by 2 plus 1 will lie between 0 to 2, and certainly f of x by 2 plus 1 will also be equals to 0. So clearly f of x will be equals to f of x by 2 plus 1 for all x belongs to 0 comma 2. Similarly you can prove for similarly you can prove for all x belongs to 2 comma infinity. What about x equal to 2? At x equal to 2, I know that fx will be equals to what? Fx will be equal to 1. And what will be f of x by 2 plus 1? F of x by 2 plus 1 will be equals to what? F of 2 by 2 plus 1, which is f2, and which is certainly 1. So clearly, this particular function satisfies this definition. F of x is equal to f of x by 2 plus 1. This functional equation is satisfied, but f is discontinuous at x equal to 2. So this statement is false. So I hope you've got a glimpse of functional equation in last 2 lectures, including this one. Uh, Tomorrow we are going to start with epsilon del approach and algebra of continuous function. I hope you're liking this series of continuous functions on real numbers. My task is to expose you to all these topics in a certain way that it doesn't consume much of your time. And once you are ready with this, then you are ready to uh, do questions from your competitive exams. So in that scenario, please let me know in the comment section if this series is helpful for you or not. Till then, take care. Bye bye.